First-order differential equations. A first-order differential equation in standard or normal form is written as the derivative of an unknown function or the dependent variable with respect to the independent variable equals a function of the two variables. The unknown function or a solution to the differential equation is a function such that its first-order derivative exists, meaning it is differentiable, and it satisfies the given differential equation, meaning its derivative equals the function in the two variables. The topic of this video are techniques of finding a solution of a first-order differential equation. A differential equation can have an explicit solution. It is expressed as the dependent variable defined solely in terms of the independent variable. Or an implicit solution. It is written in expressions in the two variables. An initial value problem is finding a solution to the differential equation that also satisfies the given initial condition, or the value of the dependent variable at a value of the independent variable. A solution is a general solution if its first-order derivative exists, and it satisfies the differential equation. Meanwhile, a solution is a particular solution if, aside from the previous two conditions, it also satisfies the given initial condition. That is, the value of the solution at the given value of the independent variable is equal to the given value of the dependent variable. Separable differential equations. Consider a first-order differential equation. If the variables are separable, the solution is found by integration. The first form is the normal or standard form, while the second form is the differential form. To be able to integrate the equation, each side of the equation must be written in terms of just one variable. Or each term of the equation must be written in terms of just one variable. Example. Find the general solution of the differential equation. Solution. The variables of the differential equation are not fully separated. Write the differential equation in separable form. So, divide the whole equation by the factor we want to separate. Rewrite using a property of exponent. Because the coefficient of each differential is in only one variable, we can now proceed with integration. The first term can be integrated using integration by parts. Let u be equal to x, and dv be equal to e to the x dx. Thus, du equals dx, and v equals e to the x. Use the formula of integration by parts. The second term can be integrated using the power rule, while the right side of the equation uses the constant rule. Express the general solution of the differential equation. Finally, find the explicit form of the solution, if possible. Note that 2k is also a constant, so write it as c. Hence, this is the general solution of the differential equation. Homogeneous differential equations. Consider a first-order differential equation in differential form. Where m and n are coefficient functions in x and y. If m and n are homogeneous, that is, if each variable is replaced by a parameter times that variable, the result is the coefficient function times the parameter raised to the same real number. The solution is found by substitution. If m is simpler, let x equals vy, so that dx equals v dy plus y dv. Or if n is simpler, let y equals ux, so that dy equals u dx plus x du. After substitution, the differential equation becomes separable. And can be solved by integration. Example: find the particular solution of the differential equation that passes through the point 2, 4. Solution: the differential equation is already in differential form. Test if it is homogeneous. Substitute each variable by a parameter times the variable. Because both tests lead to the coefficient function times a parameter raised to the same number, the differential equation is homogeneous. Because the coefficient function of dy is simpler, do substitution for y and dy. Let y equals ux and dy equals u dx plus x du. Distribute and combine like terms. The equation is now separable. Divide the equation by the factors that must be separated. Simplify. And because variables are separated, integrate the whole equation. For the first integral, apply the natural logarithmic rule. For the second integral, use the natural logarithmic rule with substitution. Combine the logarithms by using a property of logarithms. Take the exponential function of both sides. Express the general solution of the differential equation. Because y equals ux, Substitute u equals y over x. Use the given initial condition to find the particular solution. Substitute the computed constant into the general solution. And then, find an explicit form of the solution. Hence, the particular solution to the differential equation is the following equation. Exact differential equations. Consider a first-order differential equation in differential form. Where m and n are the coefficient function of dx and dy, respectively. Suppose the differential equation can be expressed as an exact derivative of an unknown function. An unknown function that satisfies the differential equations is called the general solution and is given implicitly by the following equation, where c is an arbitrary constant. More detail on how to find this solution later. In the meantime, let us focus on how to determine if a differential equation is exact. Recall that the differential of a function is written in the following differential form. It follows that, comparing the two differential forms, the partial derivative of the unknown function with respect to x is equal to the coefficient function of dx, and the partial derivative of the unknown function with respect to y is equal to the coefficient function of dy. Now there is a connection between the two forms. Because we know the given differential equation, we need a condition of exactness based on this differential equation. Suppose the first-order partial derivatives of the coefficient functions are continuous. That means the mixed second-order partial derivatives of the unknown function are also continuous. Consequently, they are equal. Therefore, a first-order linear differential equation is exact if the following first-order partial derivatives of the coefficient function are equal. In this condition of exactness, the partial derivative of a coefficient function is taken with respect to the variable of the other differential. This condition also implies that there is an unknown function that satisfies these two first-order partial derivatives that were introduced in the previous page. After proving that the differential equation is exact, let us find an unknown function that satisfies the condition of exactness, using these two partial derivatives of the unknown function. If the differential equation does not satisfy the equality, then it is non-exact. To be able to apply the method in finding the general solution in the next page, a non-exact differential equation has to be made exact, such as introducing an integrating factor into the differential equation. There will be a discussion of non-exact differential equations in the next video. The general solution can be found by using a first-order partial derivative of the unknown function. Integrate both sides with respect to the variable of the partial derivative. While keeping the other variable as constant. Now we have an expression for the unknown function, where the arbitrary function acts as a constant of integration and will be solved later. And because of the other first-order partial derivative of the unknown function, which is taken with respect to the variable that was kept constant in the previous step. It follows that the arbitrary function is the integral of the derivative of the arbitrary function, which can be taken as the difference between these two terms. After finding the arbitrary function, substitute it back into the expression of the unknown function in order to get the complete equation of the general solution. Note that we can use any of the partial derivative as the first and the other as the second, and the answer will be the same. Example. Find the general solution of the differential equation. Solution. The differential equation is already in differential form. Proceed to test if the differential equation is exact. By finding the partial derivative of the coefficient function of a differential with respect to the other variable. Because the partial derivatives are equal, the differential equation is exact. Next, find an expression for the unknown function. Substitute the coefficient function of a differential, and add an arbitrary function in terms of the other variable. Integrate with respect to the variable of integration while keeping the other variable as constant. Next, find an expression for the derivative of the arbitrary function. Substitute the computed integral from the previous step and the required coefficient function of the other differential. Take the partial derivative with respect to the variable of differentiation while keeping the other variable as constant. Cancel out the same terms on both sides of the equation. Now we have the derivative of the arbitrary function. Find the arbitrary function by integration. Integrate using the general power rule, where u equals the sine of y and du equals the cosine of y dy. And then substitute into the expression of the unknown function. Therefore, the general solution is given implicitly by the following equation. Integrable combinations. If a first-order differential equation is non-exact but resembles integrable combinations, it can be converted into exact differentials, and therefore it becomes an exact differential equation. The following integrable combinations can be written as differentials. Recall that a differential is related to a derivative through the following formula. Hence, these differential formulas have corresponding derivative formulas, such as the product rule and the quotient rule. Meanwhile, Here are additional integrable combinations that can be expressed as differentials. As stated earlier, these differentials come from derivatives. For instance, using the chain rule, the derivative of the natural logarithm of a quotient is 1 over the natural logarithm of the quotient times the derivative of the quotient. Substitute the derivative of the quotient, and then convert into a differential, which leads to the integrable combination on the left side. After writing as integrable combinations, solve the differential equation by integration. In summary, convert a differential equation into integrable combinations, which then can be written as differentials, and then can be solved by integration. Example. Find the general solution of the differential equation. Solution. Write the differential equation in differential form. Use the definition of a differential. Multiply both sides of the equation by the denominator. Divide out a common factor. And then subtract this term on both sides of the equation. Because the differential equation is now in differential form. Test if the differential equation is exact. Because the partial derivatives are not equal, the differential equation is non-exact. Proceed with converting it into an integrable combination. Distribute the differential. Now that the differential equation is written fully as sum or difference of terms, look for terms that may resemble an integrable combination, such as the sum or difference of x dy and y dx. Factor out a common factor. And combine the first and third terms. Divide both sides of the equation by the factors that must be moved in order to convert an expression into an integrable combination. This factor that transforms a non-exact differential equation into exact is called an integrating factor. The first term is an integrable combination, while the second term is ready for integration in one variable. Note that the second term can be written as a differential. Find the general solution by integrating both sides of the equation. And then simplify. Therefore, this equation is the general solution to the differential equation. Integrating factors. If a first-order differential equation is non-exact, which means these first-order partial derivatives are not equal, find an integrating factor such that when it is multiplied to both sides of the differential equation, the differential equation becomes exact. That is, the condition for exactness becomes the equality of these two first-order partial derivatives. And when the product rule is applied, the condition can be expanded into the following partial differential equation. In the following discussion, we will learn how to find an integrating factor as a function of just one variable using this differential equation. Assume the integrating factor depends on just one variable. If the integrating factor is a function of x, it follows that the partial differential equation in the previous page reduces to the following differential equation. And then, solve this differential equation by separation of variables. Hence, the integrating factor is given by the following expression, where the integrand is a function of x. In general, this formula of the integrating factor is valid if this expression consists of constants and/or the corresponding variable of the differential. Meanwhile, if the integrating factor is a function of y, it follows that the partial differential equation in the previous page reduces to the following differential equation. And then, solve this differential equation by separation of variables. Hence, the integrating factor is given by the following expression, where the integrand is a function of y. In general, this formula of the integrating factor is valid if this expression consists of constants and/or the corresponding variable of the differential. Now, suppose a first-order differential equation has a special form. If the coefficient functions satisfy the conditions of homogeneity, meaning the differential equation is homogeneous, the integrating factor can be found using this equation. If the coefficient functions satisfy these conditions, the integrating factor can be found using the following equation. Finally, if a first-order differential equation is linear, the integrating factor is given by the following formula. For additional details and examples, please watch the videos about homogeneous and linear differential equations. Example: find the general solution of the differential equation. Solution: express the differential equation in differential form. Add this term on both sides of the equation. And apply the definition of a differential. And then subtract this term on both sides of the equation. Next, test if the differential equation is exact. Find the following first-order partial derivatives. Because the partial derivatives are not equal, the differential equation is non-exact. Afterwards, find the integrating factor that will make the equation exact. Use any of the two formulas and see which one yields an equation in one variable and/or constants. Substitute the required expressions into the formula. Distribute and combine like terms. and then simplify. Because the result is just a constant, proceed to finding the integrating factor. This is the expression of the integrating factor. Verify that the integrating factor makes the given differential equation exact by taking their product. And checking that these first-order partial derivatives are equal. As the next step, apply the method of solving exact differential equations discussed in a previous video. It starts with finding an unknown function that satisfies the exact differential equation. Substitute the required expressions. The additional term refers to an arbitrary function to be solved later. Integrate with respect to the variable of integration while keeping the other variable as constant. Use integration by parts. And then, differentiate the unknown function with respect to the other variable. Substitute the required expressions. Cancel similar terms on both sides of the equation. Now we have an expression for the derivative of the arbitrary function. And then, solve the arbitrary function by integrating the derivative of the arbitrary function. Substitute the arbitrary function into the unknown function. Lastly, complete the general solution of the differential equation. Therefore, this equation is the general solution of the differential equation. Linear differential equations. Consider a first-order linear differential equation in standard form. The dependent variable and the first-order derivative are linear. The coefficient function of the dependent variable and the other side of the equations are functions of just the independent variable and/or constants. Suppose lambda as an integrating factor such that if the linear differential equation is multiplied both sides by the integrating factor, the left side of the equation can be expressed as the derivative of the product of the integrating factor and the solution of the differential equation. There are two things to consider. First, because these two terms are identical, then these two terms must be equal. Second, because these two expressions are equal, these two expressions must be equal as well. It means that the integrating factor lambda comes from the equality of the two terms, and makes the linear differential equation exact. Which means the following equality holds. Therefore, the solution of a linear differential equation is example. Find the general solution of the differential equation. Solution. Write the differential equation in standard form. Divide both sides of the equation by the coefficient of the first-order derivative. and then simplify. The differential equation is a linear differential equation. P of x is 2 over x, and q of x is the sine of x all over x squared. Determine the integrating factor. Use a natural logarithmic function rule and a property of logarithms. Note the square of an absolute value is the same as the square of that value. The integrating factor is x squared. The role of the integrating factor is that when it is multiplied to both sides of the linear differential equation, the equation becomes exact, which means the differential equation can be written in terms of an exact derivative. Through product rule and chain rule, the derivative of the product of the integrating factor and the solution leads back to the product of the integrating factor in the left side of the equation in standard form. Going back to the example, find the solution of the differential equation using the integrating factor. Integrate using a trigonometric function rule. Therefore, the following function is the solution to the differential equation. Bernoulli differential equations. Consider a first-order differential equation in standard form. Where n is a real number. If n is 0 or 1, the differential equation is linear, and the solution can be found using the method of integrating factors. If n is not 0 and not 1, the differential equation is nonlinear. However, it can be reduced to a linear equation through substitution. Start with substitution. Let u be y raised to 1 minus n, and by chain rule, du dx equals 1 minus n times y raised to negative n times dy dx. The differential equation becomes linear in the new dependent variable. Notice the main differences between the Bernoulli and the corresponding linear differential equation. Afterwards, find the integrating factor. Lambda. That makes the linear differential equation exact. Which means that if the integrating factor is multiplied to both sides of the linear differential equation, it can be further reduced in the following form. Therefore, the solution is found by integration. Where u is y raised to 1 minus n. Example. Find the particular solution of the differential equation that passes through the point 0, 1. Solution. Write the differential equation in standard form. The differential equation is a Bernoulli differential equation, with n equals 2, which means 1 minus n is negative 1. P of x is 1, and q of x is negative e raised to x. Transform into a linear differential equation by dividing both sides of the equation by the nonlinear power of the dependent variable. and applying the following substitution. Let u equals y raised to -1. Using the chain rule, du dx equals -y raised to -2 times dy dx. Write the differential equation in terms of the new dependent variable. Which is now a linear differential equation. Determine the integrating factor. And then, find the solution using the integrating factor. Integrate using an exponential function rule. Substitute u equals y raised to -1. If possible, write the solution in explicit form. Solve the arbitrary constant using the given initial condition. Substitute x equals 0 and y equals 1. Hence, the following equation is the particular solution to the differential equation at the given point. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.